Assalamualaikum. Selamat sejahtera. Good morning, everyone. All right. Okay. Yeah. There was no class yesterday due to public holiday in Johor State. Okay. Yesterday I informed you through the WhatsApp group about this one book, right? So I think it's good if if students can have a copy, some sort like as part of your mini, library. Um, if you have other calculus books, it's also good. Yeah, but in case you don't have any calculus book, to buy, I think this is a good copy, for you to have as your own. Yeah. All right. So let's see. Let's review a little bit what we have discussed. Well, let me first share computer screen.
Doctor, I just have to inform you. Because just now my friend, my friend Sam, is in this section too. He didn't come to the class because he had to go to fetch his grandfather to hospital.
I mean, that student should contact me himself or herself, isn't it?
Doctor, I'm here.
Oh, okay.
Because I'm done with fetching my grandfather just now. I haven't told.
All right.
Sorry, doctor.
All right.
Thank you, doctor.
All right. Glad to have you with us. Yeah. What is it that we discussed last time? Yeah. Can you see the computer screen? I'm sharing with you right now.
Can, doctor, can.
Okay. Yeah, I think last time we discussed this example. Discussing this example. Yeah. This is this is a test question, isn't it? This is a test question. Yeah. But before we discuss this example, let's consider another example similar to this one. Then after that, I will come back to this sample test one question here. Okay. What is that question? Is it the same? Suppose you are given this function here, w equal to f x y z equal to z minus square root of x squared plus y squared. Yeah, so this is a function of three variables, right? This is a function of three variables here. Color. Why I cannot change the color? Why I cannot change the color? Let me close this one and open it again. Okay, let's discuss this given function here. Is its range? Okay. What do you think is the domain of this function f here? Is it defined for all x, y, and z?
I think no. Just
No.
define with X and Y.
Is it defined for all x, y, and z? Are there any values x, y, and z that will give difficulties in evaluating this function f?
No,
No,
there
right?
is no restriction, I think.
Yeah. So the square, because x squared is always greater than or equal to 0 for any number x. Similarly, y squared is also greater than or equal to 0 for any number y. So the domain is the entire x, y, z. Okay. So here the domain is all points x, y, z, right? In the real or all real x and y, z. Yeah. So this function f is meaningful for all real numbers x, y, and z. Yeah. There is no points x, y, z that will give difficulties in computing this function f. Yeah. Okay, what about the range? Real numbers? Yes, isn't it? The range is can take any real number. W here can take any real numbers. Yeah. Because Z here can take any real numbers. So similarly, W here can also take any real numbers. So the range is the whole real number system. Okay, what about the graph? Can we sketch the graph of W equal to Z minus X squared plus Y squared? Is it possible? In what dimension? See, the domain is in 3D, right? The domain is in 3D while the range is in 1D. Yeah. So the graph must be in 4D, in 4-dimensional space, right? 3 plus 1 is 4. Yeah. So the graph is in 4D space. So impossible, isn't it, to graph a 4-dimensional space in our 3D world. Yeah, we are trapped in this 3D world here. So impossible for us to draw a 4-dimensional graph in our 3D world. Okay. However, we could sketch the level surfaces at various values of just like 2D, just like in a 3-dimensional graph. Okay, we could draw several level curves. So similarly, for 3-dimensional graph, we could sketch the level surfaces. It's not level curves because the level surfaces is in 3D because because it is 3D, so we call it level surfaces. W equal to K. If you recall from our previous discussion, we call this level curves, right? The graph of z equal to fxy is a 3-dimensional object. Yeah. So when z equal to constants, then we have level curves. Plane z equal to constants, it gives us level curves. Give us level curves, yeah. And for a 3-dimensional object, okay, when we intersect the 4-dimensional object with the level surfaces w equal to k, then when we slice the 4-dimensional object with the equation w equal to k, okay, then it gives us level surfaces here. Level surfaces. So so if z equal to, then we have z equal to square root of x squared plus y squared equal to k, something like this, isn't it? Yeah. So therefore z equal to k plus.
So you can see the equation.
Equation, why? I'm already sharing. Can you see? Can you see?
Can.
Okay.
Can, sir.
So why is it somebody said cannot see the equation?
Maybe he lagging, sir.
Lay? Maybe he what?
Yeah, maybe I was lagging, sir. Sorry.
Lagging.
Lagging. Oh. All right. Can you see this equation now?
Yes.
Okay. But okay, this is graph in a graph. So the graph of this equation sits in a 3-dimensional space, isn't it? Sits in 3D. Yeah. So dimensional object here. However, we could sketch the level surfaces for the object for various values of k. And the level surfaces sits in the 3-dimensional space. So if I let k equal to 0, we will get one level surface, z equal to square root of x squared plus y squared. And we have seen before that the graph of this equation is a cone. Remember, let me show you our previous note. Where is it? Where is that cone? Yeah, this one here. Okay. Squared plus y squared. Previously, and it is a cone, right? It is a cone. So let's sketch this cone. Okay, it is indefinite, right? This cone here continues upward. Yeah. So this is the cone, the level curve z equal to square. Okay, so imagine we have a four-dimensional object. When it hits our three-dimensional world, the object appears like a cone. Like a cone. Yeah. So if I now say choose k equal to -1, suppose k equal to -1, then we have z equal to -1 plus square root of x squared plus y squared. And the graph is also a cone. It's also a cone, but translated 1 unit downwards. Okay, so let me use a different color. Suppose it's still a cone, but translated -1 unit. Okay, -1 unit. Below the xy plane. If I choose k equal to say 1, then we will get z equal to 1 plus square root of x squared plus y squared. So the graph is also a cone, but it is a blue cone translated 1 unit upward. Okay, 1 unit upward. So let me draw that cone in green here. So this is z equal to 1 plus square root of x squared plus y squared. Okay, so as it intersect our world, it appears like several layers of cone like this. So recall this diagram I showed you last time when we were discussing about level curves. Okay, suppose we have this a mountain, right? Surface in blue here. Okay, so imagine when the mountain here moves and intersect the xy plane. Okay, suppose the mountain here moves and intersect this xy plane, which is the two-dimensional world. Then the intersection looks like this contour curve, right? So suppose you are living in a two-dimensional world. It's difficult to imagine a three-dimensional object. And but we could sketch the level curves here. Okay, so this level curve shows that if this mountain here, if it moves, okay, downward and intersect this two-dimensional plane or two-dimensional world, the intersection looks like level curves here. So similarly, we have this four-dimensional object. As it moves into our 3D world, then it looks like this cone here. Okay? The intersection of the four-dimensional world, as the four-dimensional object moves into our three-dimensional world, then they have this appearance of cones. All right. Yeah. So that's what level surfaces here is about for function. Okay, last time we discussed this example. Okay, so now let us finish this example. Yeah, this one here. This is a sample test one question. I have uploaded the sample test one question into the e-learning. Yeah. So let me take a snapshot of this example. Okay, we have answered the domain as well as the range. Okay, sketch the level surface of the function w equal to 0. To 0. What happens when w equal to 0 here? Then we get this equation 0 equal to z minus the square root of 1 minus x squared minus y squared. And this can be written as z equal to square root of 1 minus x squared minus y squared, right? Yeah. Okay, what is this? What is the graph of this equation? What is the graph of this equation here? This must be certainly greater than equal to 0, right? Because of the square root. Z can only take values greater than or equal to 0. Yeah. What happens? Suppose we square both sides. Then we get z squared equal to 1 minus x squared minus y squared. And when x is 0, what happens? When x is 0, this is the, what do we call it? The xy, zy trace, right? The zy trace. Zy trace. Then we get z squared equal to 1 minus x squared. All right.
XY. So
Oh yeah,
1 minus y
1
squared.
minus y squared. Yes. Oh, we have one. Is it? Oh, it's y, not y squared. Okay. I'm sorry. Should be just y here. It's not y squared. So this means y equal to 1 minus x squared minus z squared. Yeah. So when x is 0, z squared. So on a zy plane, it is parabolic, right? This is a parabolic equation here. So on a zy plane, it is a parabolic equation. When z is 0, when z is 0, y equal to 1. What else? On a zy, when z is 0, y equal to 1. When y is 0, z equal to plus or minus 1. Suppose 1 here, minus 1 here. So let's connect. Okay, so it is. So on a zy plane, it is a parabola y equal to 1 minus z squared. What else? What happens when z equal to 0? Z equal to 0, we have the xy trace. Then we have y equal to 1 minus x squared. 1 minus x squared. So when x is 0, y is also equal to 1. And then it intersect here at 1 and minus 1. Okay. And when we use a red color, when y is 0, then we have the xy, no, exact. We have the exact trace, right? Exact trace. Then we have 0 equal to 1 minus x squared minus y squared, which is x squared plus y squared equal to 1. So when y is 0, this is z. This is z. So we have x squared plus z squared equal to 1. It is a circle, right? It is a circle here. Something like this. So it is like a paraboloid, isn't it? Horizontal paraboloid.
Yes, doctor, it's probably.
Z must be greater than or equal to 0 actually. This is how the original equation looks like. So it is part of the paraboloid actually. What color should I use? Let me use the purple color. Okay, so it is actually the top part. It's actually the top part only. Not the bottom part, just the top part only. Yeah. Something like that. This is just a sketch, so might not be accurate. So just a sketch, right? So it is only the top part, okay? The portion of the paraboloid above the xy plane. Because of this, so the purple part is z equal to square root of 1 minus x squared minus y squared. That is the level surface of the object. The reason we square both sides is that so that we can see that this equation represents parabola, right? Quickly, so that we can see. The reason we square both sides so that we can rewrite it in this form, and then when we sketch the traces, we can recognize that these are parabolas and circles. Yeah, but we must come back to this original form of the equation. So we see that z must be greater than or equal to 0. So it is part of the paraboloid which is above the xy plane. Okay, so that is the solution here to this. This is a sample test one. Of this function f(x), x, y, z is a four-dimensional object. Okay, so this is how the four-dimensional object looks like when it intersects our 3D world. 3D world. It appears um, the top part of this paraboloid here. Okay, any question? Okay, so I have discussed these functions of two variables, three variables, their domains, their ranges, and also some ideas of sketching the graphs of function of two variables and level surfaces, and also level curves and level surfaces, yeah, or functions of three variables. The topic on differentiation. Topic on differentiation. If you look at our course information once again, the next topic is partial derivatives. Yeah, I have not followed this lecture plan strictly. Okay, after introducing the concept of multivariable functions, domain, and range, I went straight to graph of functions of several variables, level curves, and common surfaces, level surfaces. Yeah. So I have discussed this topic here. So next, I will discuss partial derivatives. Okay. Okay, so let's recall something about variable. Okay, suppose you have a curve, you're given y equal to f of x, so we have some curve here. So we are interested to finding the slope of the curve at this particular point here. We can determine the slope by using derivative. Right? This is what you have seen, you have studied before. And dy dx shows how y changes with x, right? Shows how the rate of change of y with respect to x. If we have x a function of t, then dx dt shows the rate of change of x with respect to time t. All right, so so how do we determine the slope of a surface z equal to fxy, say at the point P? So saying z equal to fxy, we have seen from our examples, z equal to fxy is some surface in a three-dimensional space, right? Suppose there's a point P here. Suppose we are standing at the point P on the surface. What is the slope of the surface at the point P? Now the slope varies, isn't it? It depends on in which direction you are looking at. If you are looking at this direction, then this is the slope. If you are looking at a different direction, then you may have a different values of slope. Okay, just like when you are climbing a mountain, when you reach a point at on the mountain, and then if you look around, the slopes of the mountain varies, isn't it? Depending on the direction that you are looking. So the question is, so to answer this question is in general very difficult because it depends on where you are looking at. What is the direction, the slope, which direction you want to determine the slope. Okay. So there is a formula how to determine a general formula how to determine the slope that depends on the direction. Okay, that you need to know something about vectors later on. But for now, let us look at a slope in two directions only, along the x-axis and along the y-axis. Okay, so suppose we have a surface here in blue representing z equal to fxy, and there is a plane here. We have a plane y equal to y naught here. It's a constant. Okay, y equal to y naught is a plane horizontal to the zx plane. So the plane y equal to y naught will intersect the surface along this green curve here. So the red line here is the tangent. Suppose we have a point P on the surface. The red line is the tangent, right, of the slope on this a green curve here at the point P. So here we can determine the slope in the x direction, and we define it as f partial x at the point x naught. Suppose P is at the point has xy x slope of the surface in the x direction as in this using this notation here, f partial x, for finding the slope of the surface at the point P in the x direction. Okay, so here y naught is a constant. Okay, y naught is along this green curve, y is always y naught, right? And x varies along this curve, x varies, but y remain constant equal to y naught. So we differentiate f with respect to x, holding y as a constant. So similarly here, if I want to find the slope at the point P in along the y direction, okay, we intersect this surface using this horizontal plane, x equal to x naught. Okay, this horizontal plane has the equation x equal to x naught. Yeah. So then we have a tangent. Okay, the tangent that measures the slope of the point P along the y direction, along the y direction with x equal to x naught. So on this curve, x remain constant, x equal to x naught, but y varies. So we denote the slope as f partial y, x naught, y naught. Okay, So this is the notation used for finding the slope of the surface at the point P in the y direction here. Okay, so that's the geometrical interpretation of partial derivatives here. So sometimes it is also written, the f partial x is also sometimes written as a subscript, subscript x. It measures the rate of change of y constant. Yeah. So f partial y, sometimes also denoted as f with subscript y at the point x naught y naught, measures the rate of change of the function fxy at the point x naught y naught with respect to y, holding x constant. Okay. Yeah. So this is the further explanation. So let fxy be a function of two variables. If we fix at y and let x varies, then fxy can be viewed as a function of x alone, right? Yeah. So f partial x, the derivative of f with respect to x holding y constant, mathematically is defined as this limit here. Yeah. So calculus of single variable f prime x is defined as this limit here. Limit, provided this limit exists. Okay. Just that the word used there is in Malay. So this means limit. In Malay, it is called had. This keturunan tangent means slope. Okay. This is tangent, the slope of tangent. Okay, so the formula is almost the same as for a function of a single variable here. Okay, here we y does not varies, but x varies. Okay, x varies. You see here x plus h, and h tends to 0. So that means x varies, yeah? And we think of y as a constant. So this symbol, we read it as f partial x, or the partial of f with respect to x. Yeah. Or the derivative of f with respect to x. Yeah. Similarly, if we now fix x and let y varies, then fxy can be viewed as a function of y only. So the f partial y, okay, is denoted by this symbol here. This is a curly delta. Yeah? This is a del symbol here, or sometimes written according to this formula here. Okay, so we say here that we read this symbol as f partial y, or the partial of f with respect to y, or the derivative of f with respect to y. Yeah. Okay, let's look at some examples. I cannot move this downward. I want to move it downward. I couldn't. Why is it? Why is it? Do I need to close it again? Yeah, I think that's what I need to do. Close it again and then reopen. Okay, let's look at some example. Some example of calculating partial derivatives. Suppose we are given this function, z equal to fxy equal to 2x squared minus 3x y cubed minus 6y plus 7x say minus 1. Okay? Yeah. Suppose I want to find z partial x. Okay, which can also be written as f partial x, or f with a subscript x there. So we differentiate f with respect to x, holding y constant. So that gives 4x minus 3y cubed plus 7, right? That is the answer. Okay, think of y as a constant, like the numbers 2, 3, 6, 7, minus 1, okay? Then you differentiate only with respect to x. So this is the result according to the definition. Can you tell me what is a z partial y? What is f partial y? Can somebody tell me what is f partial y?
Negative 9xy squared
negative 6.
minus 6. Minus 6.
Can you say that again? Minus
Minus
9xy squared
xy squared minus
6.
minus
6.
6.
Yeah, that is correct. Yeah. So this is some surface, isn't it? Fxy here is the graph is some surface. So in this step we assume y constant. When we're finding f partial x, we assume y constant. When we compute f partial y, we assume x constant. Okay. So suppose I then want to do is the slope of the surface at the point 0, 1 in the x direction. What is the slope of the surface at the point 0, 1 in the x direction? Then we calculate f partial x 0, 1. Okay. In the f partial x that we have computed just now, we replace we have f of x minus 3y cubed plus 7. So we replace xy here by the point 0, 1. So we get 4 times 0 minus 3 times 1 cubed plus 7. So the answer is minus 3 plus 7, which is the surface of the slope at the point 0, 1 in the x direction is equal to 4. Yeah. At the point 0, 1. When x is 0, y equal to 1, what is z? X equal to 0, y equal to 1 implies z equal to what? minus 6, minus 1, minus 7, right? Minus 7. If you substitute x equal to 0, y equal to 1, you will get z equal to 0. So to be precise, this should be at the point 0, 1, minus 7. Okay, let's have around 12 o'clock. Huh?
Hello, sir. Excuse me, sir. Sir? Hello, sir.
10 minutes break, 10 minutes break.
10-minute break though.
Okay, thank you.
Any question?
Excuse me, sir.
Yes, tell me.
Nak tanya, macam mana Z boleh jadi negatif 7, sir?
Macam mana boleh ganti negatif 7?
Saya...
Oh, ni. You see, in this equation, we are given x0, y0, right here. We are given x0, y equal to 1. So this is a point on the surface, right? So it is a point on the surface. So it is x, y, z. Only points on the x, y. Normally, if we have a point on the surface, the point is in terms of x, y, z, right? So if I replace x equal to 0, y equal to 1, I will get minus 1. Okay, let me do this again. I replace x in the equation by 0, y equal to 1, minus 6 times 1 plus 7 times 0 minus 1. This is equal to minus 7, right? Minus 7. Yeah. So the point on the surface when x equal to 0, y equal to 1 is the point P here. I can call this as a point P on the surface. Okay, this point P is on the surface. So the slope at the point P here on the surface in the x direction positive. 4 is positive here. So that means the slope is increasing in the x direction. Okay, at the point P, the slope is increasing in the x direction. So we can say that this is greater than 0. So geometrically, we can say that the slope is increasing at the point P in the x direction. Okay, let's evaluate f partial. What is the slope of the surface at the point P in the y direction? what is the slope of the surface at the point P, 0, 1, minus 7. Then we calculate f partial y. The slope is f partial y evaluated at x equal to 0, y equal to 1. What is f partial y that we have calculated just now? It's minus 9xy squared minus 9xy squared minus 6. Okay, here we replace xy by 0, 1. So this is equal to, we replace x by 0 and y by 1. So this is equal to minus 6. Okay, and this is less than 0. So what does it mean? That the slope is decreasing at the point P in the y direction. Right? It means that the slope is decreasing at the point P. So depending on which direction you are looking at, then you will get different slope. Okay? The slope may vary from one direction to the other direction. So in the x direction, you need to climb up. Okay, at the point P. In the y direction, you need to climb down in the y direction. Okay. We have what is called the gas law. Okay. In chemistry, there is a gas law for a fixed mass of n moles, okay, of an ideal gas. It's given by this formula here. P P equal to N, stands for pressure. N, and we have R T divided by V. Okay, so P here stands for the pressure. T stands for temperature. V stands for volume. Gas constant. So we can think of P as a function of two variables, T and V. Can think of P here as a function of two variables, T and V. N is constant, R is a constant, and V is a constant, right? Yeah. Therefore, what if I want to then we can measure the rate of change of P with respect to T. We have N R over V, isn't it? Yeah. And the rate of change of the pressure P with respect to the volume is equal to minus. Okay. So partial derivatives are important when you want to measure the rate of change of a function of several variables. We want to change to measure the rate of change of one variable with respect to a particular variable. Then we can use partial derivatives. In another example, we have this temperature problem. Suppose this is the x and this is 0 up to the point 120. Suppose we have a rectangular, a metal bar here, something like this. A metal bar of length 120. And suppose the temperature varies from point to point, and suppose it is equal to described by uxt equal to, for example, 100 e to the minus kt sine of pi x over 120 here. So k is some constant. Okay. Where t, we can think of t as time greater than 0. So this is like a temperature. Uxt here can be viewed as a function that depends on x as well as temperature t. Yeah. You can think of t as a time. It's a temperature function. Suppose how the temperature varies from point to point, okay, with respect to time. So if I differentiate u with respect to t, what is the answer? Anybody tell me what is the answer? What is u partial t here? Yes. We need to differentiate with respect to t holding x constant, right?
Negative 100k exponential
Yes. Yes.
negative kt sine pi x over 120.
Yeah. So here we differentiate with respect to e, with respect to the exponential function only, because the sine function is independent of t. So this is always less than 0, isn't it? Sine pi x less than 0, right? Sine as x varies from 0 to 120, sine, what is the ux0 here at this point? U 0t equal to 0, right? u0t, if I replace x by 0, we will get 0. And here at this point, u at 120t is also equal to 0, right? X equal to 120, we have sine pi, which is 0. Yeah, so the temperature is 0 at the end of the metal bar. The metal bar, the temperature is 0, but the temperature is varies. But you can see here, this is less than 0 because of the negative sign. So that means we have a cooling. Okay, we have a cooling. The metal bar is cooling as time varies. This shows that the bar is cooling at all points, which implies the metal bar is cooling at all points x between 0 up to 120. Yeah, because it's negative. That means the temperature is decreasing. Okay, decreasing. Some comment about notation. Yeah. Yeah. Some common mistakes. This is the correct symbol for f partial x, but sometimes I have seen students using this symbol here. So this is not this is not the correct symbol for f partial x. This is delta, delta, the Greek symbol delta, but this is just del or curly d. This is called curly d or just del. But this one is delta. So don't use delta when you, that is the convention. Okay. So similarly, we use del f del y for f partial y, not delta f delta y. Okay. So please make use that you use the right symbol. Okay, let's see some examples of derivative, partial derivatives. First, we are given fxy equal to e to the power of say something about x cubed y minus xy cubed times x squared plus y squared. So what is f partial x equal to? Look at the division. X cubed y minus xy cubed divided by x squared plus y squared. Okay. What is f partial x? You can apply the quotient rule that you have studied in calculus. In calculus, you have this the quotient rule for derivative, right? We have what is called like v u prime minus u v prime over v squared. This is for the quotient rule that we have studied for a function of single variable. You can use this quotient rule as a guideline. So think of this like a function of ux. both the function upstairs and downstairs here are functions of two variables. So f partial x is v. We write this as v xy. Now, instead of writing u prime, we should use u partial x. Okay, because we are talking about u here is a function of two variables. So we should use u partial x, not u prime. And minus u xy times v partial x divided by v squared. Okay. So first we have v, upstairs we have v, so it is x squared plus y squared. And then we differentiate u with respect to x, where u is x cubed to xy, which is x cubed minus x cubed y minus xy cubed times the derivative of v with respect to x, where v is x squared plus y squared, divided by the square of v, which is x squared plus y squared squared. And then we simplify. Okay. What is the partial x here? What is the partial x?
3x squared.
Partial x. 3?
3x squared.
Y. Y.
Minus y cubed.
Y cubed. Okay, that is correct. What about the second partial x?
2x.
The second partial x is 2x, huh? Okay. Then we have x squared plus y squared downstairs. And the next thing is to simplify. Okay, simplify. I leave it to you to simplify. This is mostly algebra. So show that it is equal to x to the power of 4y plus 4 x squared y cubed minus y to the 5 divided by x squared plus y squared squared. Okay, so that is the f partial x over here. Okay, so similarly, one can also determine f partial y. We use the same quotient rule, but this time we use derivative with respect to y. It is vxy uxy times v partial y divided by x squared plus y squared squared. Okay, so I leave it to you that to show that the result is x to the power of 5 minus 4x cubed y squared minus x y to the power of 4 divided by x squared plus y squared squared. Okay. So here we have used the quotient rule as a guideline to find the partial derivatives of a quotient. So as a do not write f partial x in this case like v xy times what is u x cubed y minus x y cubed. Do not use prime, okay, for partial derivatives. It's a common mistake here. Okay, do not use prime. Use prime only for function of a single variable. Then we have u, xy. Then we want to take the partial derivative of v. Okay, again, do not use the symbol prime. This is mathematically, this is not correct. Do not use prime, because when you use prime, you don't know exactly what you are differentiating with respect to. Is it with respect to x or with respect to y? yeah. So do not use a prime, okay, for partial derivative. The symbol prime is restricted to a derivative of a function of a single variable. Okay, suppose now you are given a function fxy say sine of x squared plus y squared minus xy. What is f partial x, f partial y equal to? Okay, so this is recall what you have studied about composite function. If you have like in calculus, remember how you differentiate a function. Suppose I have y equal to say f, a function of g of x. Okay, sometimes written as f composite g x. Okay, so what is dy dx? Dy dx is you still remember what is dy dx for this function? We have the outer function and we have the inner function. F is the outer function, g is the inner function. So the rule is we differentiate the outer function first, right? Then we differentiate the inner function. This is called the chain rule. Okay? We differentiate the outer function and then we differentiate the inner function. So what we have here in this example for f(x), the function is sine and the inner function is x squared plus y squared minus xy. Sometimes we also use for f, sometimes say we let u equal to g of x. So we have y equal to f of u, where u is a function of g of x, right? So when we want to calculate dy dx, we differentiate with respect to u first and then multiply by du dx, isn't it? The chain rule. What is dy du? Dy du is f prime u and du dx is g prime x. Then we replace u by gx. calculus. Calculus. So, what is u? So, the outermost function is sine. What is the derivative of sine?
Cos.
Cosine, right? It's cosine. Cosine. So f function x is cosine. First, we differentiate the outermost function, and then we differentiate the inner function with respect to x.
Is equal to.
Yeah, let me write it down first.
Okay.
So, what is that?
2x minus y.
X minus y. So we can write it as 2x y squared minus xy. Okay. So fxy, we can also think of, or we can write fxy as a function of sine u, where u is a function of two variables, x squared plus y squared minus xy. So we want to find f partial x. We differentiate sine u with respect to u. Okay? And then we differentiate u with respect to x. Thing like this. Again, we differentiate the outer function sine to get cosine, isn't it?
Yeah.
So we still have cosine x squared plus y squared minus xy times the derivative of the inner function with respect to y. What is the result?
2y minus x.
2y minus x, yeah. 2y minus x times cosine.
Times cosine.
Cosine x squared plus y squared minus xy. Okay? So here we need to apply the chain rule. Chain rule is also important for you to know when you evaluate partial derivatives. So we look at this sample question here. I think now we have enough knowledge to solve this problem number 3. So let's take this as another example. Sample test 1. Okay, how do you answer this? How do you answer this? Z is equal to f. F is some function, ln y over x. This is a composite function here. Let's show that following equation is true. Okay. So using the previous idea, use the idea used in the previous example, we can think of z here as a function of u, where u is a function of two variables, ln y over x. Yeah. You can write z in this form. So what is z partial y? Well, let's calculate z partial x first. It's equal to f prime u, isn't it? F prime u. Then we differentiate u with respect to x. We don't know what f is, so f here is some function. Okay, it's not specified here what is f here. So we can think of u as a function of a single x and y. So what is u partial x here? Anybody? Is u partial x here?
Negative ln y over x squared.
Negative ln y over x squared, right? Yeah, so we can write it as negative ln y over. Some students call it ln, some students call it ln. I call it ln. ln, yeah. Okay, what about z partial y? Again, we use the formula here, f prime u, u partial z, or u partial y. So we have f prime u, what is u partial y this time? U with respect to y, holding x constant. Ln y becomes 1 over y, right? When you differentiate ln y with respect to y, it is 1 over y. So we also have x downstairs, so it is 1 over xy. Okay, so now we go back to the expression on the left-hand side. Okay, so therefore y, z partial y plus x over ln y times z partial x. What is that equal to? You want to show that it is equal to 0. Yeah. So substitute both z partial z and z partial x into this expression. Z partial y is f prime u and z partial x is minus ln y over x squared times f prime u, isn't it? F prime u. So notice have some cancellations here. What else? Here ln y also cancel out, and 1x will also cancel out, right? So what remains is f prime u
over x
minus,
minus,
isn't it?
yes,
Minus f prime u again
over x.
over x. So the result is 0. Okay, so let's solve this question here using chain rule. The idea is chain rule here. Any question?
So far, no.
No. Okay. Let's see. Okay, let's look at another example. Suppose you are given this function here, fxy equal to x cubed minus x cubed y minus xy cubed. Maybe I use this one here. E to the power of xy times x squared plus y squared to the power of 10. Okay, but it find f partial x. What about the product rule? Okay, this looks like a product of two functions, the exponential function and the binomial function here. So we call the product rule for derivative. It's u prime v plus u v prime, right? This is the product rule for derivative. So can use this also as a guideline, okay, to find f partial x. Yeah, so here this is u as a function xy, and the second function here is a vxy. Derivative, so do not use prime. We use partial derivative symbols. Okay, so first we differentiate u, and then multiply that by v, and then plus u times dv dx. Okay, so this is actually the product rule, but instead of using prime, we use the partial derivative symbols here. What is u partial x? What is u partial x? This is also a composite function. U is a composite function. V is also a composite function here. What is u partial x? Yeah. The outer function is e, right? The inner function is xy. Then you differentiate the inner function. Let me write it in detail like this. And v is x squared plus y squared to the power of 10 plus u. U is e to the power of y. Okay, next we differentiate v with respect to x. So v is a power function, isn't it? V is a power function. So 10 times x squared plus the outer function is the power function. So that is the derivative of the power function. And then we differentiate the inner function with respect to x. So then we simplify. F e to the power of xy. The first partial x is y, right? Y. And then we have 10. The second partial is what? 2x, isn't it? 2x. So we have 10 times 2x is 20x. So I can write this as 20 x e to the power of xy times x squared plus y squared to the power of 9. And if we wish, we can factor out the exponential function and x squared plus y squared to the power of 9. So we will get y times x squared plus y squared plus 20x, right? Plus 20x. Yeah. So we can leave the answer in that form. Okay. Any question? So these are some examples of partial derivatives. Continue this again next week. Next week I will discuss higher partial derivatives. The higher, so far we have only been looking at just first partial derivatives. So far, we have been only looking at the first partial derivatives, f partial x, f partial y. There are also higher partial derivatives, just like in the calculus of function of single variable. Okay, I will discuss this more next week. Then we also have other formulas, a chain rule for function of several variables. Any question before we stop here?
So any attendance?
What?
Any
yeah,
attendance?
yeah. Also, I plan to give your first assignment tomorrow. I will inform the first assignment through the WhatsApp group, and then you can do it in groups, a group assignment. We'll give your first assignment tomorrow. Okay.
Yes, sir.
We'll give hand in. I call it hand in 1 because this is to be handed in tomorrow. This is a group assignment. Group assignment. You can do it in a group of 2 or 3 students. Yeah. Group of 2 or 3 students. Okay. One group should have 2 or 3 students. Yeah. And the first assignment will be due next Thursday next week. Okay. Post it in the e-learning or in the WhatsApp group. This will be do it in a group of 2 or 3 students, and this is due next Thursday. All right. Okay, I will also upload this lecture note in the e-learning after this. So let me first show you your attendance, a QR code for attendance. Okay, there you are.
Doktor, saya belum ada dalam grup.
Siapa yang in charge? Apa yang in charge? Saya tak tahu, bukan saya yang in charge. Jangan nak inform. Everybody here knows who is the person in charge of creating the WhatsApp group for this course? This section.
Please kindly give the number at the chat.
Okay, I give number at chat.
There's a chat room here, so yeah. Thank you. Is it Sam who is in charge?
No, sir. My friend is in charge.
Okay, you can help.
Yeah.
Okay, thank you, Sam Wong.
Saya dah send number saya dekat chat.
Okay.
Okay. Sekejap ah.
Okay, you may, for those who have already scanned, you may leave this meeting.
Hello, doctor.
Yes.